Other stories as we work our way into lunch in about 30 minutes. Yes, sir. Alexander, do you want to come on up?
Yeah,
Let's absolutely.
easy.
Absolutely. Uh, Mike Larkin was a regular figure at these events in Tokyo, and I would absolutely welcome an update. And go ahead and introduce yourself.
So my name is Alexander Blum, and I work for Genua. It's a company that creates firewalls and VPN appliances based on OpenBSD. And what we did in the previous 1 or 2 years is we were doing confidential computing. So confidential computing is a technology where the virtual machine doesn't trust the hypervisor. It has some It uses some CPU features. Of course, they are all incompatible. There's AMD, which is a straightforward design. There's Intel, which tends to be compatible with their SGX that they had to make some confidential userland applications, and that makes it very complicated. And we didn't look into that. And then there's AMD, no, not ARM. Sorry, ARM, which is doing some works. I would say they're a bit behind, and we didn't look into that either. That's just what you're hearing there. And well, what we have done is we have implemented parts of that for AMD in OpenBSD hypervisor VMM, and also for the OpenBSD client, so that we can boot it on VMM, OpenBSD, and also on KVM. So KVM has more or less full support for all that features. And all the why are you laughing? Because he was looking for how he or storage on this computer.
Hypervisor. I'm looking for your talk.
What dare you? So, okay, so there will be a talk from Hans-Jörg Höxter at Sunday, I think.
Sunday, okay.
Mhm. And but I can give you a brief overview what is there. So in AMD, the technology is called SEV, Secure Encrypted Memory. That's the basic step. So the idea is that um, every VM gets a key, and the memory is encrypted with that key, and the hypervisor can look into that memory, but it cannot make out what the guest is doing. That's the first step. Then you need ES. It's SEVES, like encrypted state, because the problem is when the VM gets stopped, then does a VM exit, then the hypervisor gets all the CPU state because it has to save it for resuming the VM. So at every interrupt or something, the VM gets stopped, and then to make that secure, you have to encrypt the data so that the hypervisor cannot the CPU state. So if, for example, in the FPU you have all your AES keys, and you don't want that the hypervisor sees that. So we have implemented that also. It's running on VMM as a host, and it's running in OpenBSD guest. What doesn't work yet is multiprocessor support. So it doesn't run on work on VMM anyway, but the guest on KVM cannot do it because it needs a different bring up code for every CPU to get it up. So we haven't implemented that yet. The next step we are currently working on is SEV SNP, Secure Nested Paging, next AMD technology. And this is about the hypervisor can read your pages, and it can also write to your pages. The memory is encrypted, but you have a block size of 16 bytes. It's AES. So you can see what the guest is doing by just looking at the memory and see, oh, this 16 bytes is changing here, it's changing here. So you can have a picture of the guest. Also, the address randomization does not work properly, because when you see where somebody is writing something, you can figure out how the layout is. And then you can say, okay, I can do a write there, and then you change 16 bytes randomly within the guest, but probably you can exploit them. Because when you figure out where the global variables is, maybe you can find a spot where you can say, okay, we write here, and then we don't crash, but we figure out now we are running as root or have no secure level or whatever. Because this is all stored in global variables. Yes?
So if you have a dual socket server how will you get your key material securely from one CPU socket to the other?
Can you repeat the question?
Okay, the question was how do we do it with dual socket servers? So the thing is that there is a PSP, a platform security processor, that's on the CPU somehow. Don't know how it works exactly. Then you have to ask AMD. And I also don't know how it's done. The synchronization is done between two sockets, but that's something the platform has to do, or it's not supported. I don't know. As a programmer, you just talk to the PSP. The PSP generates the keys and holds them within it. So the hypervisor says PSP generate a key for the VM, and then you get an ID um, that you can assign to the VM, and all the management of that stuff is done in hardware. There's also a crypto processor, which is between your memory, or in your memory controller between the memory and the CPU, which does all the cryptographic thing, and it talks to the PSP to get the keys. And the idea is that the hypervisor is not able to interfere with that. So it's abstracted from you. So I don't know what happens with dual CPU machines, because that's not a question of what the software has to do. That's somehow synchronized by the machine architecture below. So next step we have to explain is this SNP. And there the idea is that you cannot modify the pages of the guest when you are the hypervisor, because it has a reverse page table, and the page is then assigned to certain guests. And when you do a memory access, then the physical page is looked up in its reverse page table, and the processor will find out that the hypervisor doesn't own the page, and so it will get a page fault or exception, some sort of exception. So that's how SEV is working. We are currently Hans is working on the IO MMU support, because you need a working IO MMU to get SEV running. Probably because otherwise the devices could write into the memory, and we have to protect the memory. But the details are somehow kept in the hardware, so you just have to set it up that it works. And the fourth thing you will have to do is some sort of attestation. So the trust model is that you get some third party which says, okay, this VM is running on in this by this hyperscaler and on this CPU, and it's trusted, and nobody can look into that. So the attack would be to have an QEMU or some other single stepping machine, and this one would say, oh, I'm trusted here, and trust me, I run in a supervised or in a trusted confidential environment, and you have to prove that this is the case. But the QEMU cannot prove it. So the idea is that the guest has access to the PSP, the platform security processor, gets out some cryptographic signature that it is running on some of a real authentic AMD processor. Maybe there is also a key from the hyperscaler who says, okay, I'm running at Amazon cloud. I'm not sure how it works. We didn't implement that yet. So the idea is that you can prove that you are running on a real processor that has all the security requirements to make it secure, and you run where you are supposed to run, and not somewhere at the NSA in a broken environment. And so you need a trusted machine where you make this cryptographic key exchange between the authentication server and the guest. So you can scale your guests somewhere in the cloud and have one physical machine that makes sure that every guest is truly running confidential. And the way it might be done is, for example, when you have an encrypted hard drive, and all the keys for the hard drives, for the hard drive encryption is at the authentication server. Then the guests when they boot, they go to the authentication server and say, "Hello, I'm running on a real confidential CPU. Trust me. Here's my certificate. I can sign it. It has been signed by the CPU." And then the authentication server would give back the key for the hard drive, and then you know that only trusted guests can see the hard drive. And if the hyperscaler just boots another one where he can look in by not enabling the feature, it cannot authenticate itself and will not get the key for the hard drive. So that's the idea what could be implemented. So just a little overview.
Other questions? And it sounded like you're waiting on, be it SMP or other features. Is this work in progress? Is there something we can try today?
So question is, what we are waiting for, if we are trying to get other features. So what we are currently doing is gating the basic things in. Goal is to run our appliances in such trusted environments. We build firewalls. We want to have a trust anchor in some hardware. SMP is a thing for us. So probably, so we our main goal is to run in KVM. And there SMP is working. We just have to adapt the OpenBSD guest a little bit that it can do it, but just adding the bring up code for the CPUs. But this is one track, just getting our appliances running. But the other thing is that we want to have it incorporated in OpenBSD, and there we want to go together with their hypervisor, with VMM. So we implement it in VMM, and we implement it in our in the guest. And the big advantage of this approach is that we understand it. So if you run something on KVM, you set some bits in the kernel and then something works. But here Hans-Jörg Höxter is implementing the guest side and the hypervisor side. And so you get a real understanding which bit you set here, what affects here. And of course, we don't implement the full feature set. So VMM in OpenBSD can run OpenBSD as a guest, and it can run Linux more or less. So I run Linux there, but I've never tried another operating system, and I think it wouldn't work. So even FreeBSD doesn't work, I think. So we have a limited feature set, but we try to get everything that is needed for all the security in there.
What AMD CPU generations or categories have the SEV support?
It's only the server CPUs. You cannot get it on a laptop, and it's the newer ones. I'm not exactly sure where it comes. So all the things I found in my lab somehow can do it, but they also do it in steps. So the oldest ones can only do SEV, the newer ones can do SEV ES, and then SEV SNP are already newer ones. So it's an evolution of their feature set together with the evolution of implementing all the stuff. You start with the basics.
Other questions? Awesome. Thank you so much. I appreciate that. Thank you.
How much overhead is there to enabling this shoes? How much runtime overhead is there?
Oh, the overhead. Yes. Go ahead and repeat that.
So the question is, how much overhead is there? You see, we have the FreeBSD conference. People are talking about performance. So AMD claims it's 2%, maybe true for all the memory encryption. But the main thing is when you do DMA, you have to do bounce buffering. So you have the encrypted page within your guest, and you want to get it out. Currently, we support VirtIO. Maybe it would be possible to support other devices, but VirtIO is sufficient for all that. So you have to get it out to an unencrypted thing that's done by the guest, because only the guest is trusted. So for each DMA page, you have usually the one within the guest is encrypted, and you allocate a second page that's unencrypted, and you copy it over. So when you read here, it gets unencrypted to the CPU, and the other one is the other page is mapped in clear text. So it's just a mem move from the one to the other, and that costs me in my networking test 10 to 20%. So, and it doesn't really matter of if you turn off this memory encryption or not. So I have a feature in the kernel where I can just set a define to turn off this turn on this bounce buffering all the time, and there you clearly see the overhead of copying memory in and out. And I do networking tests because that's my usual work, making OpenBSD network stack going MP. So I have a lot of testing of that, and there it hits to with 10%, 20%, because network is very heavy in copying in or out. If you're just mining bitcoins, probably I think it is not relevant. Or except when you use GPUs, then you still have the problem that you have to move to your GPU. I was at the Confidential Computing conference there. They talk about confidential GPUs, where you want to protect your training data and your queries to the AI. There they start doing encrypting the PCI bus and then authenticating the GPU. Also, the GPU has a secret and kind of transfer it to somewhere and sign it with something. And it's all very complicated. And we are just getting the basics with the CPU in, and it's enough work.